Okay, so right now we're going to be working with convergence and probability. So the first thing we want to know is that this, right, is equivalent to this. So x of n being equal to x of 0 plus OP1 is equivalent to saying that x of n converges in probability to x of 0. And that also means that the limit, right, this is the actual formal note, the formal, definition of it, that the limit of x of n minus x of 0, the absolute value of that is to be greater or equal to epsilon being a really small value. If you're unaware on how this thing works, I'll put a video under the description that I watched that really helped me. It's a lecture from a guy from MIT, really well made. It explains it in a really nice, concise fashion, so you guys can understand it. So now we're given this exercise, right? X of n is equal to this, and this will imply that the function applied to x of n and x of 0 will also be, convergent in probability to f of x of 0. So how do we prove this? Well, the first thing we have to do is, we focus on this guy, right? So this guy must imply, right, that this, just edit this. First of all, we're going to remove the epsilon here. I'm going to write a delta because they cannot be the same value. Now let's just rewrite this. Oops. I forgot this guy. Okay, perfect. F of n minus f x of 0. And this has to be absolute value, so let's make it a bit with more space. Right, this is what we want to prove, right, basically. And so we can focus on this little guy here. What does this equal to? So let's copy this and let's paste it over here. Right. So what does this equal to? Well, we can remember that the law of total probability, if we remember the law of total probability, right, this would be equal to k I1 A given BI times BI, right? This is the law of total probability we would normally use. However, we have to remember that that this, right, that this can be equal to, let me just erase the I. This can be equal to the probability of A intersection B, right? So that means and, this is an and, right? Meaning that if we have all of that, meaning that we have this, we can rewrite this as saying, let me just write this here, right? We can rewrite it as taking A, which is in this case, well, this thing, and just write it with another color so we can understand it a bit more clearly. This is going to be A, right? And then we're going to take P, and this is going to be the sum, right, of all the, meaning, let me just explain this. From here, we're going to go through here, and we're going to say the K I equals 1, and then it'll be P A intersection of BI, right? Meaning that we can simply say the BI in this question is going to be this guy, right? This is going to be I. This is going to be BI. So I'm going to write B, this is going to be A, right? This event, so to speak. So what we do now is saying, okay, I'm going to take A. So I just take A. And intersection is going to be just and. So we're going to put a comma as an and. And we're going to write the B1. So B1 is going to be this guy. Right? And this guy. Plus, we're going to copy the same thing. Right? We're going to copy the same thing. But this time we're going to do the complement. What do they complement? Because we have the different cases, which is by BI, is B1 and B2 in this case. We have two cases, so the complement of this, right? So given that, we can continue on. And as you can see, we have two different sections. So let's mark them with different colors, okay? This one is going to be red. Oops. And this one is going to be blue. So for this guy, what do we do? Well, we have to just check something out. We have to see the following, okay? We have to understand that this event, I'll just copy it real quick. This little event, right? I'll just write it as this. Is going to be a subset of, simply put, this guy. And you're going to be asking like, why? Why is it so? Okay. So to understand this is saying, okay, we have this condition, and on top of that condition, let's just say these are the same. As you can see, these are the same. But on top of that, we have another condition that has to be like satisfied, meaning that this is already this, but this makes it a subset. So this will be now a subset of this, simply put. And by monotony, we remember that the probability, right, of this guy is going to be lower or equal to the probability of that guy because they're subsets. And now if we take limits on both sides, limit as n approaches infinity of this little guy, right, has to be lower or equal to the limit of n approaches infinity of this guy over here. Oops. Right? Now, this part, we have to understand that this goes to 0 because this is simply what we had earlier. So this thing is the same thing that we stated over here, right? Which is given here. So we're just implying, assuming that this is true. So this will be equal to 0, meaning that this whole thing is lower or equal to 0. And as probabilities have the rule that they cannot be negative. The only thing that we can conclude is that this is equal to 0. Oops. This is equal to 0. And as you can see, we're done with the red part, right? Now let's do the blue part. So 4, and now we take this guy here, copy, paste, and put it here. Now what does the blue part say? Well, we know for a fact that, we just have to understand something real quick. So let's take, let me just think. Yep. So if we take this guy, right? Then it means, right? This will mean, by law of continuity, that fx of n minus fx of 0 is going to be lower to epsilon. Why is it so? Hold on, let me just rewrite this. Why is it so? Okay, let me just grab something real quick. Totally forgot to take my notebook out here too, because I have a note right there that explains it. There we go. We have to understand that this is a direct result of continuity, right? meaning that closeness, closeness, this means closeness. The closeness in inputs leads to closeness in outputs. So if it's a continuous function, a closeness in inputs will lead a closeness to outputs. So let's give you an example. Imagine we have 1 minus, I don't know, something really small, 0.99, right? 0.99, this is going to give you 0.1, right? So this is what we have, right? And 0.1, let's say, again, imagine we're taking for this case, just so you can understand what I mean. Let's take for this case that x of n is equal to 1, x of 0 is equal to 0.99, and delta equals, I don't know, again, 0.15, right? So 1 minus 0.99, this will give us, right? This will give us 0.1 is, 0.1, sorry. 0.01 is lower than 0.15, right? Now let's take that f of x, let's take that f of x is equal to, I don't know, 2x, which is a continuous function. So with this same logic, this is going to be 2. Fx of 0 is going to be, 0.99. I don't have my calculator, but I have my calculator here on my phone. So we can take 0.99 times 2. That's going to give us 1.98, meaning that 2 minus 1.98 is going to be lower than, let's just say that this is times 2 again, so 0.3. So epsilon in this case is going to be 0.3. So in this case, we're going to have 2 minus 1.98, 0.02 is still equal to this, right? So as you can see, this is true. Doesn't matter what we do, as long as a function is continuous, this is true. So this is what I wanted to show, right? So closeness in inputs will lead to closeness in outputs. So we can just directly state the following, state that. Now that we have that, this would contradict this. Why? Let's take this and copy it over here. As you can see, we have different signs. They're going like against each other. So if this is true, right, then we know that it's true by assumption, then we apply it, and by the continuity, this will also be true. And this little guy is the opposite of this guy. So the probability of this and this being true is equal to 0 in that case. So we can say that the limit of the blue section as it approaches infinity, right, is going to be equal to 0. So as you can see, we have both limits already done, right? So we can take that the limit, right, we can just copy it and paste it here. We can say that the limit as n approaches infinity is going to be 0. This is going to be for the red part, plus 0. This is going to be for the blue part, is equal to 0 when we have proven thus that that this is equal to 0, meaning that fxn is equal to fx of 0 plus op1. It's a bit more, this was kind of a complicated exercise, but basically what we're working with is first, what we first do is, let me just write it with another color. I don't like this color. Let's do orange and yellow. Let's do yellow. We first find complements. We'll find the law probability, and we decompose, basically. Decompose with the law probability. look at limits of the compositions of the compositions, apply, and then done. And then you're done, basically. So that's basically what we have to do, right? We first took this guy. We applied the law of probability, which is over here. Yes. Then we have two little sections that we have to analyze. So we analyze the red part first. And by monotony, we were able to finish this quite nicely. And also with blue, same situation. We have this, which is just like contradicts each other. So we can say that the limit of that is 0. So once we apply the limit on our left side, which is the original thing we want to decompose, it'll be 0 plus 0 is equal 0. And then we have our end result. That's it. Okay, so now we are taking the following exercise, right? Let me just write it. Approaches 0 as n goes to infinity, which leads to x of n going to OP1. What does this mean, right? This means basically, this just is another way of writing, right? This is just another way of writing that the limit of this little guy, the limit of this little guy as n approaches infinity is equal to 0. That's it. And then this guy, we want to prove what we want to prove, right, is that the limit of the probability of x of n being greater than epsilon equals to 0 as n approaches infinity. So over here, we're going to use a really, really, really nice and cool feature called the Markov's inequality. So let's write here. Markov's inequality, which states, right, that if I can find it here, Markov's inequality is really, really easy. It's really nice. It's like the best. I really like it. So the Markov's inequality says that for any probability z, right, being greater or equal to epsilon, must be equal to the expected value of epsilon over its epsilon counterpart. That's it. This should be lower than equal, right? That's simply put the end of it. It should be lower or equal than that. So simply put, hold on. Markov's inequality. Let me just check something real quick. Maybe I did something wrong, guys. Yeah, sorry. Markov's inequality is this, right? So in this case, we're going to let z be equal to simply put the x of n, right? So x of n squared, meaning that the probability of x of n squared, right? Well, actually, let's just do something easier like that. Let's just write it like that. Then the probability of z greater than epsilon has to be equal to the probability of x of n epsilon, right? Now we know for a fact that if we squared both sides, then we squared by both sides, so we get, right, and this will be lower or equal to the expected value of the x of n squared of epsilon squared. That's simply put what we're doing here. Now, as we know, the limit, let's just take the limit of this. So the limit of this little guy, the limit of n approaching infinity, right? Of this whole chunker. We duplicate it, we make it smaller so it fits. This will approach 0. Why? Well, we can rewrite it so you can understand it better. We're going to write 1 epsilon 2 because it's not dependent on n times the limit of this expected value, right? And this one is equal to 0. Therefore, times 0 is going to be 0. Therefore, we can say that the limit of this guy as n approaches infinity must be lower or equal to 0. Now, as we know for a fact, simply put, we know for a fact that we can remove the squares and that will not affect our computing. So this will indeed turn into the limit. And because limits are cannot, like, as probability is going to be negative, we remove the 2 here, the squared, and we can simply say that this is equal to 0. And just like that, we have proven that x of n is equal to OP of 1. Again, we use Markov's inequality, and the why we can actually like remove the square and it doesn't affect our computation is because the only thing that would change would be this e squared, and we can just remove that, simply put, So yeah, that's pretty much how we did it to solve this one with Markov's inequality. The next exercise that we're going to be solving is this guy. So we're saying this big OP of 1, and that y of n is also big OP of 1, which would lead to x plus yn equaling to OP of 1, the big OP. Now we have to understand something, right? OP of 1 means, for any variable, it means, let's just take z of n, or z. It would mean that z of n is limited by a c, and the probability of that is 1 minus epsilon. That's basically what we want to prove. So in this case, we have a sum, right? We have a sum. So this sum is this guy here. So what we do, first of all, is declaring what we know. We know that x of n is this. Let me just duplicate it. Let me just erase this, actually. We duplicate this guy, which implies, well, this is equivalent to saying that the probability of x of n, c, 1 minus epsilon, probability yn, c, 1 minus epsilon. All good, all perfect. Now the thing is we want to prove this guy, right? And this guy would state, right? This guy would state that x of n plus yn, I think it was, plus yn, oops, being lower or equal to c, 1 minus epsilon. Now, the thing here is what we want to do is do a little trick. As you can see, this epsilon is like just 1 minus epsilon, and we have just a constant. However, what we want to do is that when we add these two, we're going to get two constants different. So what we want to do is actually denote these. So c of x, c of y, and this we're going to divide by 2, right? So we can add up to just 1, so to speak. Now that we have that, we would say by triangle inequality, we know that the triangle inequality states the following, right? It will just state the following, that x of n plus y of n is lower than x of n plus y of n, right? meaning that we apply the probabilities, right? X of n plus y of n is going to be greater than c. Why? Because we're taking the complement, right? We're taking the complement of this. The complement of this guy, right? So we're taking the complement, then it means that that this is going to be x of n plus y of n c. Then we can, as possible, we can just rewrite this and just copy it. And we can rewrite it as two different inequalities. C of x, right? Plus probability of y of n c of y. That's pretty much it. And we know for a fact that, that this guy, right? This guy is lower or equal to what? We know for a fact that if this, let's take the complements here. So we take complement, complement, and complement. We know for a fact that we take the complement. This would be in turn just this. X and oops. C of x is going to be lower or equal to e over 2, right? And we take the same situation with y. We just replace the y's, right? Meaning that if we just add these up, we're going to have, right, which equals to e. Meaning that this guy, right, is going to be lower or equal to e. So we take the complement, right? Complement case would be something like this. And as you can see, we're done. That's it. That's what we wanted to prove, so to speak. That's literally what we wanted to prove. So it's really not that hard. It's just that the steps are, simply put, dividing the e between two cases and two complements, so we can have a singular complement over a singular c, sorry, not complement. So what we do again, we have this guy. So what we want to do is divide it by two things. So we have these two. Then we have cx and cy, and cx plus cy will give you c, right? And so what we say is, okay, now we're going to take the case we want to prove, right? And we're going to take the complement. So as you can see, this is the complement, and this is the complement, right? Once we take the complement, we have this guy by triangle inequality, right? And the triangle inequality will give us this, and then these two guys via the complement, we can find them that there will be e divided by 2, e divided by 2, and the sums of these two is going to be e. So these two guys have to be lower than e, and as this has to be lower than this, then this also has to be lower than e. And then we take the complement case once more. So it's a lot of complementations, so to speak. We have c, this is the complement of this, and this is the complement of this, and we have finished our proof. In this case, why do I keep opening that? That's it. So yeah, it's a bit bothersome, but it's doable. So yeah. So this is the last exercise we're going to be doing. So we want to prove that if x of n, given x of n, right? And just do x of n, equal to small op1, it implies that x of n is also big op of 1. So we rewrite what this means. So this means that the limit of x of n will be, well, the probability of x of n being greater than epsilon will go to 0 as n approaches infinity. That's the formal notation. And then this guy is for the big OP, which which states that the probability of x of n being lower or equal to c will be greater or equal to 1 minus epsilon. So what we do is simply we take this and we take the complement, right? So the complement is, well, this is going to be equal to 1 minus its complement. That's pretty easy. Then we see that that this guy here, we're going to take this guy and we're going to put it over here, right? And we're going to see that as it approaches infinity, it will approach 0 because this is simply put the definition over here, right? This is the definition. Same thing, just in this case we have c, we have c equals to epsilon, right? So meaning that the limit of this little guy, right, as n approaches infinity, is going to be equal to 1 minus 0, simply put. So this is going to be equal to 1. Now that we have that, we know that for any limit, right, for all epsilons greater than 0, right, there exists an n0, right, such that for all n equal n0, right, p x of n will be lower to epsilon. We have proof first that this is a limit, right? And because this is a limit by the roots of the limit, we know that for all epsilons greater than 0, there exists a point for which, if we go further, then this will be true, right? So the complement case will be true. Meaning that if we take the other complement case, right, this is going to be equal to this. Right? And we have proven it. That's simply put what we do. It's really not hard. It's kind of annoying to understand, but it's right there. And this is because of the rules of the limits. If you're confused as to how this works, again, watch the video I stated earlier about the guy on the lecture. It's really good. It's like 8 minutes long, 10 minutes long, and you understand all this stuff way easier in a more intuitive way. So that's all the exercises done, and that's pretty much it.